Article 250.30(7) of the National Electrical Code addresses conductors entering a building. It specifies that conductors entering a building must not be installed in raceways, cable trays, sleeves, or other enclosures inside the building unless they terminate within a main, service disconnect, or similar equipment located at the point of entry. In a scenario where feeder conductors for one tenant space pass through a 400 amp panel in another tenant space before reaching their own disconnect, this violates the requirement that feeders must terminate at the point of entry. This configuration also presents several common sense violations and potential hazards. Firstly, the arrangement creates a potential hazard if maintenance or repairs are needed on either tenant space's electrical system. For example, if a fuse blows in the 400 amp panel, it could affect the power supply to both tenant. Secondly, the routing of feeders through another tenant's panel could also pose safety concerns if the wall between the spaces is damaged or penetrated. To properly address this issue, consider installing a separate meter socket and disconnect for each tenant space. This would provide each tenant with its own independent electrical service and eliminate the need to route feeders through another tenant's panel. This arrangement ensures that each tenant has a dedicated electrical system, simplifying maintenance and enhancing safety. Let's delve deeper into the implications of Article 250.30(7). The primary intent of this code requirement is to ensure that service conductors are isolated and protected as soon as they enter a building. This minimizes the risk of faults or damage affecting multiple tenants or areas within the building. By requiring immediate termination in a service disconnect or similar equipment, the code ensures that overcurrent protection is readily available at the point of entry. Now, let's examine the potential hazards associated with routing feeders through another tenant's panel. One significant concern is the lack of control and coordination over the electrical system. If a fault occurs in the panel through which the feeders are routed, it could disrupt power to both tenant spaces. This can lead to operational disruptions, safety hazards, and potential damage to equipment. Another concern is the potential for unauthorized access or modifications to the electrical system. If one tenant has access to the panel that feeds another tenant space, there is a risk of tampering or improper modifications that could compromise the safety and reliability of the electrical system. Furthermore, the routing of feeders through another tenant's panel can complicate maintenance and troubleshooting efforts. When issues arise, it may be difficult to isolate the source of the problem and determine which tenant's electrical system is affected. This can lead to delays in restoring power and increased costs for repairs. In addition to these practical concerns, the routing of feeders through another tenant's panel can also create confusion and uncertainty regarding responsibility for the electrical system. It may not be clear who is responsible for maintaining the panel, replacing fuses, or addressing any other electrical issues that may arise. This lack of clarity can lead to disputes and delays in resolving problems. Now let's move on to the recommended solution of installing separate meter sockets and disconnects for each tenant space. This approach ensures that each tenant has a dedicated electrical service independent of the other tenant. This separation of electrical systems provides several benefits. Firstly, it eliminates the risk of a fault in one tenant's electrical system affecting the other tenant. Each tenant has its own overcurrent protection, so a fault in one system will not disrupt power to the other. Secondly, it simplifies maintenance and troubleshooting efforts. Each tenant's electrical system is isolated, making it easier to identify and resolve any issues that may arise. Thirdly, it provides each tenant with greater control over their electrical system. Each tenant can manage their own power consumption, install their own equipment, and make any necessary modifications without affecting the other tenant. In addition to these practical benefits, installing separate meter sockets and disconnects also ensures compliance with the National Electrical Code. This helps to protect the safety of the tenants and the building occupants. Let's also discuss the specific requirements for installing separate meter sockets and disconnects. The meter sockets must be installed in accordance with the requirements of the local utility company. The disconnects must be sized appropriately for the load served and must be readily accessible to the tenant. All electrical work must be performed by a qualified electrician and must comply with all applicable codes and regulations. The installation of separate meter sockets and disconnects is an essential step in ensuring the safety and reliability of the electrical system in a multi-tenant building. This approach provides each tenant with a dedicated electrical service, simplifies maintenance, and enhances safety. By adhering to the National Electrical Code and employing best practices, the electrical system can be designed and installed in a manner that minimizes risks and promotes the well-being of the building occupants. Let's now focus on the relevant sections of the National Electrical Code that pertain to service entrances and feeder installations in multi-tenant buildings. Article 230 of the National Electrical Code covers service entrances, which are the conductors and equipment used to bring electricity from the utility company to the building. Article 225 covers outside branch circuits and feeders, which are the conductors and equipment used to distribute electricity from the service entrance to various points within the building. Several specific requirements in these articles are relevant to the scenario of routing feeders through another tenant space. Section 230.2 specifies that each building or structure must have its own service entrance, unless certain exceptions apply. This requirement is intended to prevent the sharing of service conductors between multiple buildings or structures, which could create safety hazards and operational problems. Section 230.40 specifies the number of service entrance conductors required for a building or structure. This section requires that each service entrance have a sufficient number of conductors to carry the load served, and that the conductors be sized appropriately for the load. Section 230.70a requires that the service disconnecting means be readily accessible and located at a readily accessible location either outside of a building or structure or inside nearest the point of entrance of the service conductors. This requirement is intended to ensure that the service disconnecting means can be quickly and easily accessed in case of an emergency. Section 225.30 specifies the number of feeders or branch circuits required for a building or other structure. This section generally requires that each building or structure have its own feeders or branch circuits, unless certain exceptions apply. Section 225.32 requires that each feeder or branch circuit have a disconnecting means that is readily accessible and located at a readily accessible location. This requirement is intended to ensure that the feeder or branch circuit can be quickly and easily de-energized in case of an emergency. In addition to these specific requirements, other sections of the National Electrical Code may also be relevant, depending on the specific details of the installation. It is important to consult the National Electrical Code and other applicable codes and regulations to ensure that the electrical system is designed and installed in a safe and compliant manner. Let's now consider some of the potential consequences of violating the National Electrical Code requirements for service entrances and feeder installations. Firstly, a violation of the National Electrical Code could result in a fine or other penalty from the local electrical inspection authority. Secondly, a violation of the National Electrical Code could create a safety hazard that could lead to injury or death. Thirdly, a violation of the National Electrical Code could invalidate the building's insurance policy. Fourthly, a violation of the National Electrical Code could make it difficult to sell or lease the building. It is therefore essential to ensure that all electrical work is performed by a qualified electrician and that all applicable codes and regulations are followed. Now let's discuss the importance of proper overcurrent protection in electrical systems. Overcurrent protection is the use of fuses, circuit breakers, or other devices to protect electrical circuits from excessive current. Overcurrent can be caused by a variety of factors, including short circuits, overloads, and ground faults. If overcurrent is not properly controlled, it can lead to overheating, fires, and other hazards. The National Electrical Code specifies detailed requirements for overcurrent protection in electrical systems. These requirements are intended to ensure that electrical circuits are adequately protected from overcurrent and that the overcurrent protection devices are properly sized and installed. The National Electrical Code requires that each electrical circuit be protected by an overcurrent protection device that is rated to interrupt the maximum available fault current at the point of installation. The National Electrical Code also specifies the types of overcurrent protection devices that are permitted for use in different applications. For example, fuses are generally permitted for use in all types of electrical circuits, while circuit breakers are typically used in branch circuits and feeders. In addition to these general requirements, the National Electrical Code also includes specific requirements for overcurrent protection in certain types of electrical equipment, such as motors, transformers, and generators. It is essential to consult the National Electrical Code and other applicable codes and regulations to ensure that the overcurrent protection in an electrical system is properly designed and installed. Let's explore the different types of overcurrent protection devices available and their applications. Fuses are overcurrent protection devices that contain a fusible link that melts and opens the circuit when the current exceeds a certain level. Fuses are available in a variety of sizes and ratings, and they are typically used to protect electrical circuits from short circuits and overloads. Circuit breakers are overcurrent protection devices that use a mechanical mechanism to open the circuit when the current exceeds a certain level. Circuit breakers are available in a variety of sizes and ratings, and they are typically used to protect branch circuits and feeders. Prime fault circuit interrupters (GFCIs) are overcurrent protection devices that are designed to protect people from electric shock. GFCIs detect small leakage currents to ground and quickly interrupt the circuit, preventing electric shock. Arc fault circuit interrupters are overcurrent protection devices that are designed to protect electrical circuits from arc faults. Arc faults are dangerous electrical discharges that can occur when insulation on electrical wiring breaks down. ASIs detect arc faults and quickly interrupt the circuit, preventing fires. It is crucial to select the appropriate type of overcurrent protection device for each application, based on the specific requirements of the electrical circuit and the potential hazards involved. Proper overcurrent protection is essential for ensuring the safety and reliability of electrical systems. Let's now shift our attention to the importance of proper grounding in electrical systems. Grounding is the connection of electrical equipment and circuits to the earth. Grounding is essential for protecting people from electric shock and for preventing damage to electrical equipment. The National Electrical Code specifies detailed requirements for grounding electrical systems. These requirements are intended to ensure that electrical equipment and circuits are properly grounded and that the grounding system is properly sized and installed. The National Electrical Code requires that all metal enclosures for electrical equipment be grounded. This includes metal boxes, cabinets, raceways, and other enclosures. The National Electrical Code also requires that the neutral conductor in an electrical system be grounded. The neutral conductor is the conductor that carries current back to the source. Grounding the neutral conductor helps to stabilize the voltage in the electrical system and to provide a path for fault current to flow back to the source. In addition to these general requirements, the National Electrical Code also includes specific requirements for grounding certain types of electrical equipment, such as motors, transformers, and generators. It is crucial to consult the National Electrical Code and other applicable codes and regulations to ensure that the grounding system in an electrical system is properly designed and installed. Now let's delve into the different types of grounding systems used in electrical installations. There are several different types of grounding systems, each with its own advantages and disadvantages. The most common type of grounding system is the equipment grounding system. In an equipment grounding system, all metal enclosures for electrical equipment are connected to a common grounding electrode. The grounding electrode is typically a metal rod or plate that is buried in the earth. The equipment grounding system provides a low impedance path for fault current to flow back to the source, helping to quickly trip over current protection devices and prevent electric shock. Another type of grounding system is the grounded neutral system. In a grounded neutral system, the neutral conductor in the electrical system is connected to the earth. The grounded neutral system helps to stabilize the voltage in the electrical system and to provide a path for fault current to flow back to the source. A third type of grounding system is the isolated ground system. In an isolated ground system, certain sensitive electrical equipment is isolated from the rest of the grounding system. This helps to reduce electrical noise and interference, which can improve the performance of the equipment. It is important to select the appropriate type of grounding system for each application, based on the specific requirements of the electrical system and the potential hazards involved. Proper grounding is essential for ensuring the safety and reliability of electrical systems. Let's further examine the role of the grounding electrode conductor (GEC) in electrical systems. The grounding electrode conductor is the conductor that connects the electrical system to the grounding electrode. The grounding electrode conductor must be sized appropriately for the size of the electrical system. The National Electrical Code specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor must be made of copper or other corrosion-resistant material. The grounding electrode conductor must be securely connected to the grounding electrode. The grounding electrode conductor must be protected from physical damage. The grounding electrode conductor plays a critical role in the grounding system, providing a low impedance path for fault current to flow back to the source. A properly sized and installed grounding electrode conductor is essential for ensuring the safety and reliability of electrical systems. Now let's discuss the requirements for bonding in electrical systems. Bonding is the connection of metal parts of an electrical system to create a continuous electrical path. Bonding is essential for preventing electric shock and for ensuring that overcurrent protection devices will trip quickly in the event of a fault. The National Electrical Code specifies detailed requirements for bonding in electrical systems. These requirements are intended to ensure that all metal parts of an electrical system are properly bonded and that the bonding system is properly sized and installed. The National Electrical Code requires that all metal enclosures for electrical equipment be bonded. This includes metal boxes, cabinets, raceways, and other enclosures. The National Electrical Code also requires that all metal water pipes and gas pipes be bonded. Bonding metal water pipes and gas pipes helps to prevent them from becoming energized in the event of a fault. The National Electrical Code also requires that all metal parts of a building structure be bonded. Bonding the building structure helps to create a continuous electrical path and to prevent voltage differences from developing between different parts of the building. In addition to these general requirements, the National Electrical Code also includes specific requirements for bonding certain types of electrical equipment, such as motors, transformers, and generators. It is important to consult the National Electrical Code and other applicable codes and regulations to ensure that the bonding system in an electrical system is properly designed and installed. Now let's examine the different methods of bonding used in electrical installations. There are several different methods of bonding, each with its own advantages and disadvantages. One common method of bonding is to use bonding jumpers. Bonding jumpers are short lengths of wire that are used to connect metal parts of an electrical system together. Bonding jumpers must be sized appropriately for the size of the electrical circuit. Another method of bonding is to use metal raceways. Metal raceways, such as conduit and electrical metallic tubing (EMT), can be used to bond metal enclosures for electrical equipment. When using metal raceways for bonding, it is important to ensure that the raceways are properly connected to the enclosures. A third method of bonding is to use grounding bushings. Grounding bushings are used to bond metal conduit to metal enclosures. Grounding bushings provide a secure and reliable connection between the conduit and the enclosure. It is important to select the appropriate method of bonding for each application, based on the specific requirements of the electrical system and the potential hazards involved. Proper bonding is essential for ensuring the safety and reliability of electrical systems. Let's discuss the concept of impedance and its role in electrical systems, especially in relation to grounding and bonding. Impedance is the opposition to the flow of alternating current AC in an electrical circuit. Impedance is measured in ohms and is represented by the symbol Z. Impedance is a combination of resistance, inductive reactance, and capacitive reactance. Resistance is the opposition to the flow of current due to the material's properties. Inductive reactance is the opposition to the flow of current due to the presence of an inductor. Capacitive reactance is the opposition to the flow of current due to the presence of a capacitor. In grounding and bonding systems, it is crucial to minimize impedance to ensure that fault current can flow quickly and easily back to the source. High impedance in the grounding or bonding system can slow down the flow of fault current, which can delay the tripping of overcurrent protection devices and increase the risk of electric shock. To minimize impedance in the grounding and bonding system, it is important to use conductors that are sized appropriately for the size of the electrical circuit. It is also important to ensure that all connections are clean and tight. Furthermore, it is important to minimize the length of grounding and bonding conductors. Now, let's discuss the importance of electrical inspections in ensuring the safety and compliance of electrical installations. Electrical inspections are conducted by qualified electrical inspectors to verify that electrical installations comply with the National Electrical Code and other applicable codes and regulations. Electrical inspections are typically required for new electrical installations, as well as for renovations and additions to existing electrical systems. The purpose of an electrical inspection is to identify any potential safety hazards and to ensure that the electrical system is installed in a safe and compliant manner. Electrical inspectors typically check for a variety of things, including proper wiring methods, proper overcurrent protection, proper grounding and bonding, and proper clearances around electrical equipment. If an electrical inspector finds any violations of the National Electrical Code or their applicable codes and regulations, they will typically issue a notice of violation. The notice of violation will specify the violations that were found and will require the homeowner or contractor to correct the violations within a specified time frame. It is important to take electrical inspections seriously and to correct any violations that are found promptly. Electrical inspections are an essential tool for ensuring the safety and compliance of electrical installations. Let's discuss the importance of using qualified electrical contractors for electrical work. Electrical work can be dangerous, and it is important to hire a qualified electrical contractor to ensure that the work is done safely and correctly. A qualified electrical contractor is a contractor who is licensed and insured to perform electrical work. A qualified electrical contractor has the knowledge, skills, and experience to perform electrical work safely and in compliance with the National Electrical Code and other applicable codes and regulations. When hiring an electrical contractor, it is important to check their license and insurance to make sure that they are qualified to perform the work. It is also important to ask for references and to check the contractor's reputation with the Better Business Bureau. Hiring a qualified electrical contractor is an essential step in ensuring the safety and reliability of electrical installations. Now, let's discuss the importance of electrical safety training for individuals who work with or around electricity. Electrical safety training is essential for protecting individuals from the hazards of electricity. Electrical safety training provides individuals with the knowledge and skills to work safely with or around electricity. Electrical safety training typically covers a variety of topics, including the hazards of electricity, proper wiring methods, proper grounding and bonding, proper use of personal protective equipment, and emergency procedures. Electrical safety training is typically required for electricians, electrical engineers, and other professionals who work with electricity. However, electrical safety training is also beneficial for anyone who works around electricity, such as maintenance workers, construction workers, and homeowners. There are a variety of electrical safety training programs available. Some programs are offered by trade schools, community colleges, and universities. Other programs are offered by private training companies. It is important to choose an electrical safety training program that is reputable and that covers the topics that are relevant to the individual's job or responsibilities. Let's discuss the use of personal protective equipment (PPE) when working with electricity. Personal protective equipment is essential for protecting individuals from the hazards of electricity. Personal protective equipment includes a variety of items such as gloves, eye protection, and footwear. Electrical gloves are used to protect the hands from electric shock. Electrical gloves are typically made of rubber or latex and are rated for different voltage levels. Eye protection is used to protect the eyes from electrical arcs and flashes. Eye protection typically includes safety glasses or goggles. Footwear is used to protect the feet from electric shock. Footwear typically includes safety shoes or boots with non-conductive soles. It is important to select the appropriate personal protective equipment for the job being performed and to inspect the equipment before each use. It is also important to use the equipment properly and to follow the manufacturer's instructions. Now, let's discuss the importance of lockout/tagout procedures when working on electrical equipment. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. Lockout/tagout procedures involve disconnecting the power supply to the equipment and then locking and tagging the disconnect switch to prevent it from being turned on. The lockout device is typically a padlock that is used to secure the disconnect switch in the off position. The tagout device is typically a tag that is attached to the disconnect switch to warn others not to turn on the switch. Lockout/tagout procedures are essential for protecting workers from electrical shock and other hazards. The Occupational Safety and Health Administration (OSHA) has specific requirements for lockout/tagout procedures. It is important to follow these requirements to ensure that workers are properly protected.